Alright, let's continue. Okay, let me open the table of content first. Alright, we are on chapter 21, Beyond Physical Memory Mechanism, and we are still on homework measurement here. Let me open that. Yeah, this chapter is about swapping, I guess. Okay. Using the VM stat here. Let me open that. Alright, VM stat. I think only one. Okay. Yeah, we can just do this. And then, if I remember correctly, we can do this every 1 second, and the count is 10, maybe something like that. Bottom mem here. Well, let's try with the 1 megabyte memory. Alright. And then this one, I guess. Oh, no. Okay. Where is it? VM Beyond, okay. Alright. Okay. Let's see. Okay. What is the information again? Prox is the information about number of runnable process, I assume after the input output, maybe something like that. And then P here is number of block process waiting for the input output to complete. Okay, interesting. From that information, at first it looks like we have one. Okay. Oh, there's a difference here. Okay. Alright. I assume this one is after we run the script or the program, I guess, the simulation. Okay, interesting. So it increase and then decrease and then increase, something like this. Oh, okay. And then decrease again. Okay. I wonder, is the R or the R here increased because of the script. Maybe, maybe between these. I'm not sure. Let me try running without the script again. Oh, interesting. Right. Maybe it is because of the what is it called? Running the script. Maybe. And the pig is in here. Interesting. Now I wonder. Okay. Oh, right, wait. After 10, maybe let's try 20, I guess. Wait a minute. So we have the runnable information here, at least one. Okay. Oh, there's a two header. Interesting. Okay, maybe the second header, when we run out of space, something like that. Maybe. Okay, I guess this is when we run the script or the simulation, right? Okay. And then the memory. SWPD, the amount of swap memory use, free the amount of idle memory, above the amount of memory use as buffer, and then case the amount of memory use as case. Oh, should I use the test A option here? Let me check. But yeah, it is only, I assume, Linux kernel 2.5.41 version or better, or later, maybe something like that. Display active and active memory. Well, let me try understanding this. Is there any difference here? This one is before, I assume before running the script or the simulation, and then this is when we run the script or simulation. Okay, the free memory or the idle memory. That make me wonder, what is the difference between idle memory and inactive memory? Let me check. The difference between idle memory and inactive memory. to check this article, but I'm not sure about the copyright. Okay. Total memory statistic. Okay. Don't know, is there a way? Maybe not this one. Let's check this out. Memory management is a cornerstone. Okay. Whether you're a system administrator, that make me wonder too. Is it only in the Linux operating system, or maybe we have VMstat in other operating system such as OpenBSD or FreeBSD? I'm not sure. Whether you are a system administrator, developer, or DevOps engineer, understanding how Linux allocates, use, and reclaim memory is critical for diagnosing bottleneck, optimizing application, and ensuring system stability. Well, let me copy this to the chat, I guess. Because anyone wants to read this. Optimizing application and ensuring system stability. One of the most powerful tools for monitoring memory behavior is VMstat, Virtual Memory Statistic, which provides real-time insight into system memory, swap, input, output, and CPU usage. While VMstat is widely used, its output, especially when running with the -A, active or inactive flag, can be confusing. I guess even without the -A flag, it is still confusing. The active and inactive memory columns in particular often leave users scratching their head. What's the difference between active and inactive memory? Are they used or free? Right? How do they impact performance? In this blog, we will demystify active and inactive memory, explain how the Linux kernel manages them, and break down the VMstat -A output to help you interpret this matrix like a pro. Okay. VMstat is what is VMstat and why use VMstat -A? VMstat is a command line utility that reports statistics about system memory, process, interrupts. We have information about interrupts too. Okay. Patching, block, input, output, and CPU activity. I wonder what the patching information looks like. Yeah, I'm still not sure. Is it in the memory? I assume it is in the memory section here. But yeah, I am not sure. It's lightweight and provides a high-level overview of system performance, making it a go-to tool for diagnosing memory and input-output issue. By default, VMstat outputs column like SWPD, the swap use. In my case, we didn't use swap at all, I guess. Okay. Or the free memory, right? Or the buffer case. Oh. Is this another case? Yeah. Okay, maybe. And then case, the pets case. Alright. However, to dive deeper into memory behavior, we use the -a flag, which adds to critical column, inactive memory, and active memory. Yeah, I wonder if active memory the same as the use memory, I guess. But yeah, and also inactive memory. What is the difference between that and free memory? Okay. This is how we run the VMstat CLI. Time in second between updates, and then the count here, number of updates to display. It is optional. If we didn't provide that, it will run indefinitely until we interrupt that. Okay, active memory, the hot page. Okay, active memory refers to physical memory page that have been recently accessed by process and are considered hot. Recently accessed, okay, meaning they are actively in use or likely to be used again soon. Okay, the Linux kernel prioritizes keeping this page in physical memory. To avoid the performance hit of fetching them from slower storage like disk or swap. Okay. Interesting. Recently accessed. Actively in use or likely to be used again soon. Okay, characteristic of active memory. Recently accessed page. It is page in active list have been accessed within a recent time window determined by the kernel LRU algorithm. I kind of forgot what LRU means. Yeah, I think we talked about that previously on the scheduling, maybe, or briefly. Yeah, maybe. Maybe in this one. Let me check. Okay. What LRU stand for? Nothing. Yeah, I kind of forgot where I get the term LRU previously. LRU policy stands for least recently. Okay, least recently used. Alright. Least recently used. Okay. That is the recently accessed and then not easily reclaimable. The kernel avoids swapping or freeing active paths unless absolutely necessary, as they are critical for current process performance. Okay, not easily reclaimable. Avoid swiping or freeing active paths unless absolutely necessary, as they are critical for current process performance. Okay. Part of the page case. Active memory is often part of the page case. The cache column in VMstat, which store frequently accessed file data or process data. Okay. So there is that. Memory use as case. So there are two different, what is it called? Memory use category, I guess. Memory use as buffer and memory use as case. Maybe something like that. Hello, Param. Welcome. Is this for a class? No. This is not for a class. This is for fun, I guess. In active memory, the code page in active memory consists of physical memory pages that have not been recently accessed. Wait a minute, be right back. Okay. In active memory consists of physical memory pages that have not been recently accessed and are considered cold. Okay. These pages are candidates for reclaiming. Oh. Either by swapping to disk or freeing. Okay, if the system needs more memory for active process. Alright, key characteristic of inactive memory. Not recently accessed page here haven't been accessed for a while, making them lower priority for retention in physical memory. Eligible for reclaim, the kernel can swap inactive paths to this if they are anonymous paths like process, heap or stack, or freedom if they are file back paths like catch file to free up memory. Oh, okay. Interesting. Still useful. Inactive memory isn't wasted. It's cache data that might be needed again. The kernel retains it to avoid rereading from this if the data is accessed later. Okay. The relationship between active and inactive memory. The list, there's the term here. Least recently used. Okay. So active is the recently accessed memory, and inactive is the memory that have not been accessed for a while. Okay. And might be needed again. Alright. So yeah, maybe that is the difference here between inactive memory and idle memory or free memory here. If it is free memory, then we are not using that memory at all. But inactive memory here is like maybe a cold case or something like that. The memory that not been accessed for a while, but we might be need that again later. Maybe something like heap, like we allocate the heap memory, but we are not using that heap memory recently. Maybe I'm still trying to figure things out here. Okay, the Linux kernel manages active and inactive memory using a least recently used or LRU algorithm, which maintains two lists for each type of memory page, fileback and anonymous. Two lists for each type of memory page. Active list contains hot page or recently accessed. Inactive list contains cold page not recently accessed. Maybe I can put that in the information here. In the question, maybe. Yeah. What is the difference between idle memory and inactive memory? In VMstat, there's a report, maybe something like that. Idle or free memory is the memory that's not being used. but the inactive, I guess, is the memory that's still allocated but have not been used recently. Maybe the example of inactive memory is the heap memory that we allocated but not being used yet. Question mark. Because I'm not sure if this example is true or not. Hello, pattern name. Keep your journey up, mate. Greetings from Russia. Oh, hello. Welcome. I'm currently trying to learn operating system by reading this book, Operating System 3 Easy Peasy, and currently on chapter 21 here, trying to understand about swap mechanism here, the swap space, by looking at the Homburg measurement here, basically using VMstat to check the virtual memory statistic, and while running this simulation. Yeah, something like that. So that's why I'm trying to understand about the output of the VMstat program here. And I'm kind of curious what is the difference between idle memory and inactive memory. And well, I'm trying to make some kind of guesses, I guess, hypothesis. Maybe the inactive memory is something like the heap memory that we allocate but not use yet. Maybe, I'm still not sure. That's why there's a question mark here. Okay. And let me put that reference here. Okay, something like this. Not recently accessed. How page move between lists? Promotion to active. When a process access an active page, the kernel promotes it to the active list, marking it as hot. Oh, when a process accesses the inactive page, the kernel promotes it to the active list. Okay. Demotion to inactive. If an active page isn't accessed for a period of time, right? The kernel demotes it to the inactive list. Okay. Balancing the list. The kernel ensures the active list doesn't grow too large by evicting the least recently used active page to the inactive list when needed. Okay. The LRU-based balancing ensures that the most critical or those hot pages stay in memory, while less critical or cold pages are available for reclaim. Decoding VM-stat-A output of field-by-field guide. Let's break down a sample VM-stat-A output to understand its column with a focus on active and inactive. Okay, interesting. Memorization, focus inactive and active. Oh, is it in kilobyte? I thought this was byte. Okay. Amount of free physical memory, right? Amount of memory swap out to this. Okay. Memory used for block device buffer. For example, metadata for file system, and then case here. Memory used for the page case, file data, executable code, etc. Okay. Cold page and then hot page. Not easily reclaimable. Okay. Other key column context. Number of process waiting. Number of process waiting for runtime. CPU contention indicator. Okay. Number of process in uninterruptible sleep. You're waiting for input output. Okay. Yeah, this is basically waiting for the CPU to pick up this process again, right? Swap in or out, data swap into memory, data swap out from memory, if I remember correctly. Right, SE is swapped in, SO is swapped out from memory. Okay. Yeah, swap in into memory, swap out of memory. Okay, block input output. Oh, blocks read from this. This one. KB byte receive from a block device. In case anyone wondering what KB byte means, this is basically the binary representation. So there's a decimal representation and there's also a binary representation. representation, something like this. And I think this is to power 10, maybe something like that. Let me try. Yeah, to power 10. Okay. Yeah, that's not the case. Something like this. This is the, what is it? Gigabyte, I guess. This is kilobyte. Just something to keep in mind. Okay, receive from a block device and then send to a block device. So maybe in and out, block in and block out, maybe something like that. Hey, wait a minute. Send to a block device. Oh, okay, maybe read and written is the right term here. This is read from the block device, and this is written to a block device. Alright, something to keep in mind. Oh, there's number of interrupt per second, including the clock. I'm still not sure what this means. Like including the clock. Okay, number of context switches per second. Number of context switches per second. Oh, we have quite a lot of context switches. Interesting. Alright. And this is interrupt. Oh, there's a lot of interrupt in here. Maybe the clock interrupt is the hardware interrupt. Maybe something like that. Yeah, I'm still not sure about the interrupt mechanism here. I mean, we talked briefly about that in the scheduling here, I guess. Making sure that the operating system did not lose control over the CPU or something like that. So there's a constant interrupt from the hardware side, I assume. I'm not sure if there is a software interrupt too, but maybe there is. So yeah, that is something to keep in mind. Practical example interpreting VM state -A in real scenarios. Let's analyze 3 common scenarios to see how active and inactive values inform system health. There's mosquito. Okay. Let's analyze 3 common scenarios to see how active and inactive values inform system health. Healthy system, normal activity. Okay. No swapping use. Quite. We have some free memories, I guess. Oh. I'm not sure what is the indication of this healthy balance, Active pets are more than inactive pets. Oh, okay. But there is room to reclaim inactive memory if needed. No swap activity indicating no memory pressure. Indicating no memory pressure. Interesting. Okay. Inactive memory. Normal casing. This is normal activity. And this is normal casing. Okay. Wait a minute. Why is this confusing? Okay. See, this is supposed to be the heater, right? But suddenly it have the value. Like, what is going on? This is the heater, but then this is the value. It's like combining this together, I guess. Okay. Inactive. I guess this one. 600 megabyte is much larger than active. Okay. Oh, this is still normal. Okay. The kernel is caching file data that hasn't been used recently. Inactive, but retains it to speed up future access. Okay. If a new process needs memory, the kernel can free inactive page without swapping. Okay, memory pressure active. Hide, swap in or out. Now this is even more confusing. This is the heater, but this is the value. Okay. So is this one, I guess. So is being used. Very little free memory. Active page, okay, with the low inactive page, I guess. Most memory is active, leaving few inactive pages to reclaim. Some in or out activity indicates the kernel is swapping to free memory for active process. Sign of memory pressure. The kernel is swapping to free memory for active process. Okay, so maybe we only use swap if the free memory is not enough. Is that it? We are swapping to this if the free memory is not enough. Maybe. I'm still not sure. I'm still trying to figure things out. Why active or inactive Yeah, there is mosquito here. Why active or inactive memory matters for system health. Understanding active and inactive memory helps diagnose memory pressure. If active is consistently high, free is low, and SI or SO are non-zero, the system is under memory pressure and may need more RAM. Cache efficiency. High inactive memory indicates effective caching. The kernel is reusing data. Low inactive may mean frequent cache miss. Oh, okay. Interesting. Slower performance. Okay. Swap behavior. Inactive memory acts as a buffer against swapping. Okay. If inactive is large, the system can avoid swapping even when free is low. Common misconception about active and inactive memory. Inactive memory is wasted memory. This is false. Okay. Inactive memory is cache data the kernel retains for future use. It's not wasted. It's a performance optimization. The kernel frees it only when needed. Misconception 2. High cache means memory is full. Oh, okay. False. The cache memory includes both active and inactive memory. Most inactive cache can be reclaimed, so available memory is roughly free plus buff plus cache, not just free. Oh, wait, is this? Oh, available memory. Okay. Available memory is roughly free plus buff the memory used per buffer cache and the batch cache. Okay. Not just free. Active memory is always in use. Oh, not exactly. Okay, interesting. Misconception 3. Active batch are recently used, but a process might not need them again. However, the kernel assumes they'll be reused and prioritizes keeping them. Now I wonder if we allocate the heap memory, is it gonna be in the active memory or inactive memory? Yeah, I'm still not sure, but this is something to keep in mind, I guess. Active memory is not always in use. It is just recently used. Okay. I mean, if that is the case, is the memory in the case section here means that it is the memory that in use? I mean, if I remember correctly, right? Memory used for the batch cache. Is this the memory that is in use? or maybe put off this. But I assume, yeah, maybe put off this. Maybe memory use, right? Again, I'm trying to figure things out here. Conclusion: active and inactive memory are critical component of Linux memory management strategy, governed by the LRU, the least recently used algorithm to balance performance and resource efficiency by using VM-stat-A. You can distinguish between hot active and cold inactive paths, diagnose memory pressure, and optimize system performance. Remember, active memory is hot or recently used or hard to reclaim. Inactive memory is cold, not recently used, easy to reclaim. Oh, maybe using the heap memory as an example is not really a good example. Maybe the stack memory. Yeah, maybe the stack memory that we allocate. Yeah. The stack memory that we allocate previously, but have not been used recently. So we can claim that memory when needed, when we need some memory. Okay, and it looks like active memory does not mean the memory in use. Does not mean the memory in use. It means the memory is recently accessed. It may be something like this. And might be accessed, and might be needed later on. Yeah, maybe the active memory, maybe the heap memory is considered an active memory, something like that. So we just recently accessed to heap memory, but it is not in use, might not be in use or something like that. Like heap memory. maybe. So yeah, I'm still not sure about the example of active memory and inactive memory, but I guess that's some. But I guess, yeah, that might be an example of it. The active memory is like the heap memory that are recently accessed, but we haven't freed that yet. It is not access anymore. Not in use, but have not been freed yet. Maybe something like that. And the inactive memory, yeah, maybe the stuck memory. So when we need memory, we can replace those memory in the stack or something like that. But yeah, I'm not sure if that is a good example here. Okay. Alright. So how do the CPU uses statistic change when running mem? I don't think there's that much difference, I guess. These are percentage of total CPU time. Okay, you know what? I guess let's continue this on the next session. Okay, so I guess that's it for now. Yeah, we will hopefully start exploring the VM stat again, the VM stat output again. Maybe with the test A flag. Alright, so that's it for now. Thank you for watching and see you next time. Bye bye.